Hello everybody, welcome to this WEkEO training for atmosphere. I'm Alexandre Brun from Noveltis and I will be presenting you this Jupyter notebook exercise. So today's topic is the atmosphere and more importantly precipitations. Of course the atmosphere is a key regulator in the Earth climate. And when we talk about atmosphere, we think about temperature, precipitations, and of course changes in such patterns directly affect, first of all, the environment, ecosystems, but also human lives and activities. So this is why it is absolutely crucial to, in our case, understand precipitation patterns because of climate change. They should probably change in the future with potential impacts on agriculture, human infrastructures, and natural ecosystems. So in this workshop, we will use Python to analyze precipitation data and particularly extreme precipitation events. So this will be our key focus, and we will try to identify major changes that could happen in future climate scenarios. And of course, having such predictions gives us guidelines to implement environmental policies and so on. So, as I said, we will be working with Python. So to set up our Python environment, here is a list of the main libraries that we're going to use. So we're going to use NumPy for computing arrays in Python. Xarray is the main library that is used to open scientific data, which is usually stored in a netcdf format. So this is the library used to open netcdf files. With Matplotlib and Cartopy, we will draw the different maps and plots that we're going to need. And GeoPandas we will be used to process geospatial data. I've also mentioned rastereo, but I think that in the end, in our case, we won't be processing any satellite images or other raster data. But it's always useful to have that in our toolbox because it is often needed in environmental studies and in remote sensing applications. Using this cell, I will import all those libraries. So if you're working on the WEkEO Jupyter Hub, make sure to use the WEkEO Lab Jupyter kernel. So you can select it through this menu, because it has all those libraries pre-installed. So now to access the data. So here's a brief presentation of the data that we're going to use. So the WEkEO product that we are going to use is the simulation from Copernicus. It's called CMIP5 Daily Data on Single Level. So you can click on this link to open the WEkEO page on the data. So basically, the CMIP5 is a gathering of several experiments that were made under several climate scenarios. And what we're going to do is we'll be comparing two scenarios. So one that is called the AMIP experiment. So I think I'm presenting it right below this section. So you can just go to the dedicated RF5 page that is referred to here. So this is the home page. And so, as I said, we're going to compare two experiments. So one is from the AMIP ensemble, so Atmospheric Model Intercomparison Project. We're taking one from a French model. And basically this experiment fairly accurately represents current climate. And we were going to take another experiment, which is from the ensemble experiments from the representative concentration pathways. So those represent several scenarios depending on the amount of greenhouse gas and carbon dioxide that are emitted in the atmosphere. And we're going to use the 8.5 scenario. So which is basically in the IPCC the reference for the worst case scenario in terms of carbon emissions. So basically we'll compare our current climate to an extreme case of climate change. And so to go into more details, so here is a summary of the model that we are using, the experiment, that we are using. So we have daily data, which is the preferred temporal resolution to process precipitation data and derive extreme indicators. So here is the model that we have used. There are several available. We chosen this one that is a French model. Here is the spatial resolution, and those are the two temporal coverages of each of our experiments. So for our simulated current climate, we have data going from 1979 to 2009. And for our simulated high CO2 climate, we have data going from 2006 to 2205. So now to retrieve the data with WEkEO. So there are articles in the WEkEO website to guide you. But here is a cell that you can quickly execute, and that should do the trick for you. So first you need to make sure that you have this file, .hdARC, in your home directory in your WEkEO Jupyter Hub account. If you don't, well, you just have to execute this cell, and it will make you enter your WEkEO credentials and write them in your file. That way you will be able to access the WEkEO catalog through this Jupyter notebook through Python. So once this is done, that you have this file ready with your credentials specified in it, you should be able to download the WEkEO data. And to do that, you have to write data requests and send them through Python. So here's a brief overview here. Basically, in order to copy paste a request for data set. So for example, if I do that here on the SEMIP5 daily data on single level. So on the WEkEO data viewer. So here is my dataset in the WEkEO data viewer. And if I enter all the parameters that I want to retrieve, so here is the AMIP experiment that I've told you about. I want to retrieve the precipitation data from one of the models. So let's take this one. This is the experiment ensemble member. So not everything will be available depending on the previous parameters. For one period, I think this is the one that we had in this training. And once this is completed, you can click on Show API Requests, and it will generate this for you. So back in the Jupyter notebook, in the data directory, you can see that I have two JSON files. So basically, you can just, if I open them with the editor, you can see that I have copy-pasted the data request in such a file and saved it in the JSON format. And now with WEkEO, sorry, in my Jupyter notebook, I can open it and print it here, and this data request will be used with the WEkEO API to search the dataset and retrieve it. So in my case, I have already pre-downloaded the data, so the two files are here. You can see that this one is the one that goes from 1979 to 2009, and this one from 2006 to 2205. So you can see that there is a clear difference in sizes due to the number of years that are in each file. So let's take a look at the data. So to start, we will just look at the current climate dataset. So as I've mentioned earlier, we're using the XRA library to open the netcdf file. And so this is what we have when we open it first with Python. So you can see that this is a 3 or 4 dimension dataset with 3 main coordinates. Mainly we have a time coordinate, of course, and also latitudes and longitudes. We have also this bounds dimension that we're going to drop very soon because it will bother us when processing the data. As well have those time, latitude and longitude bounds that we have no use for, so we will drop them in a few sections. And here, this is the precipitation variable. So by clicking on this icon, you can display the metadata of the variable. So you can see that there are a few more details about the variable. So you can see here mainly the unit, so kilograms by square meters by second. It's a precipitation flux. And here are a few more attributes for the whole data set, so the date of creation, the source. So if you're interested, you can read it in detail. So as I've mentioned, in order to ease our processing, we want to work with a dataset that only has longitude, latitude, and time dimensions. So to put it simply, we're going to drop the variables, so the time bounds, lat bounds, and long bounds. And next, what we also want to do is to compute the total daily precipitation. So, as I said, our precipitation data is in kilogram per square meters per second, and we want to have the daily precipitation in millimeters. So basically, kilogram per square meters is equivalent to millimeters. So we just have to multiply the flux by the number of seconds in the day, which is 86,400. And you can see that just by doing this operation, I have assigned a new variable, so total precipitation, in the dataset. So here there is no metadata because I haven't specified any. And one last thing we want to do is to change the format of the time variable. So if we look at it here, I don't think we see. Yes, we can see how it is. In Python, this is quite of a weird format. One format that is a lot more convenient to use is a datetime format, and this is what we're doing here. So basically, I create a variable designed to store the time converted to datetime, and then I reassign it to the time coordinates. And you can see now that we have a different format that is more common in Python and that most libraries can work with. Okay, so now our data has been pre-processed. We are ready to perform the computation that we are here to do. So first of all, let's simply draw a map of global precipitation patterns and see what we have. So basically, we'll just be drawing a map of 1 day of precipitation, here the 1st of October in 2005. This is just an arbitrary example, you can easily change the date if you want to. So here it's just all about the plot. Here I'm just creating the figure, drawing the coastlines, drawing the grid, adding the land, but I don't, yes, and coloring the map according to the precipitation data. So it's in millimeters, and well, this is just a map for this date. You can easily change it. Okay, so now let's go deeper in the analysis and let's compute extreme precipitation indicators. So the extreme indicators that we're going to compute are standard ones. There are a list of them here in this in the European Climate Assessment and Dataset project. So you can visit the page if you want to know more about the other indicators, but here is the 3 that we are going to use that are quite common. So first is the SDII. It's the mean precipitation. It describes the mean precipitation amount every year, using only wet days. So day without precipitation don't count in this mean. We have the R20 millimeters, so it is the frequency of very heavy precipitation days, so above 20 millimeters. So you can see on the map here that there are not a lot of areas on this day that are above this amount of precipitation. And finally, the RX1 day, which is for every year the highest 1 day precipitation amount. So in a case, it's basically the for each year the maximum value of precipitation, because we have daily value. But for instance, you have another indicator that you call the RX5 day, which is the highest 5 consecutive day precipitation amount. So this is something that you can also compute by yourselves if you are doing this tutorial and that you have some time to experiment. So you will see all the indicators here. Let's go to precipitation. Can I find it? Should be humidity. So here is the SDII, R10 millimeters, R20 millimeters, RX1 day, RX5 day. And you have a lot of other ones. Feel free to try to compute them along with those other functions. So you can see that for RX5 day, 1 day, for example, I'm just basically computing for each year the maximum of the precipitation, total precipitation. And so we're computing each of those indicators on using our dataset that we have just opened before. And now what we're going to do is that we will compute the climatology, so basically the mean over time of each indicator over the whole 30-year period that we have retrieved from WEkEO. And that way we will be able to compute the climatology of each indicator over the whole period. And that's what we are doing here, for example. So here is the example we be with the R20 millimeters, so the frequency of very heavy rain days over the 30 years of current climate. So here our unit is the number of very heavy days during 1 year. And you can see that in tropical regions, especially here Southeast Asia, there are a lot of areas that have more than 30, even sometimes 50 very heavy rain days in our current climate simulation, which is quite a lot, and it's also quite what we expected given this region of the globe, which are indeed known to have very humid climates. Same for here, Central Africa, for instance, or here near in South America, and of course in the Central Pacific. So now we want to compare those indicators, so of extreme precipitation, with future climate predictions. So will those extreme events be stronger? Will they be more frequent? That's what we're going to investigate. So as I've mentioned, the second scenario that we are using is the RCP 8.5. So it's a scenario from the Intergovernmental Group for Investigating Climate Change, the IPCC. So as I said before, RCP 8.5 is described as a worst case scenario in terms of carbon emissions. So this time the simulation is computed using the same model, but with different inputs concerning, of course, carbon dioxide forcings, and it's done over a different time period. And we've compared the climatology of 30 years. We're also going to select only 30 years here. So from 2129 to 2159. So as you've seen before, the dataset here, as it is longer, takes more time to open. So I'm just going to pause the recording because it takes a few seconds to open. Okay, so now it is the processing is done, and you can see that we have the same time, latitude and longitude dimensions, and same as before, we have those bounds, dimensions and variables that we want to drop, and we have our precipitation fluid. So this is a very similar data set, only with different parameters, different yes, time period and so on, but the format is the same. Whoop. Sorry, I had forgotten to execute a cell, but it should be fine now. Okay, so just like before, I've dropped the bounds variable, computed the total precipitation, and converted the time coordinate. Once again, takes a few seconds. Okay, so our second dataset has been totally pre-processed. Now we can resume our analysis. So here you can see that for our second dataset, I will apply exactly the same functions to compute the extreme precipitation indicators. And here performing the mean over time using the mean function of X-array to compute the second climatologies. So over the future simulated period. And now we are simply going to subtract for each indicator the two climatologies, so SDII, air 20 millimeters, and RX 1 day, and see the variations and how they are distributed. Okay, so this is the mean intensity of precipitation days. So here you can see that near the equator we have they tend to increase in future climate, but there are areas where they decrease, here in the Saharan or Australian desert, in Southern Africa, here in Central America. This is also quite intense. So it's a mean loss here, for example, of about, I don't know, 4-5 millimeters in Central America. And here near the equator we have sharp increase. And we can see that for the frequency of heavy rain, there is a similar pattern, although it is not as intense as in the previous indicator. And here we can see that the maximum values of precipitation daily precipitation in a year have a very sharp increases in future climate almost all over the ocean, and here also in Southeast Asia. But we have also a few areas where it decreases by several dozen millimeters. So here in Central America, here in North Africa, and in the Middle East, and in Australia also. So we can see that in a climate change, the impacts on precipitations are not equally distributed spatially, geographically. So it would be wise to focus on analysis on particular regions, and this is the focus in our next section, in which we focus on regional changes. So basically what we're going to do is that we're going to retrieve data from the IPCC, because they have defined climate regions. So we retrieved it from here. So you can see that we have several reference regions defined by the IPCC. So we've retrieved here as a shapefile these reference climate regions, and using the GeoPandas library we can open shapefiles like this one. So you can see that this data of the reference regions is basically a table, so with a long name here, an ID you would say, with 3 letters, and other indicators, and a geometry, because those are the parameters of each of the polygons that we can see on this map. So you can see that we have 33 different regions going from the Arctic to the Antarctic, with Pacific regions, Asia, Europe, America. And we can print it by ourselves very easily, just using the plot function directly on the geodataset, and enabling the boundary plot only draws the contours of the polygons. So here we've drawn the coastlines just like we did before on the other indicators, and here we've plotted the regions, so you can see that they are consistent with what we had in this graph here, in this figure here. So now we're going to choose one of them and clip the climatologies that we have, the datasets that we have analyzed before, to have them only delimited to a specific region. So in our example, we will choose the Mediterranean region here, and see how its precipitation patterns are impacted. So here we write the 3 characters of this column to make sure that we select the Mediterranean region. And we compute all those variations for each indicator on this region. You can see here that we select based on the label that is called MED, M-E-D. And another thing is that we are a little more precise here, because we don't just subtract 2 mean climatologies, but we compare the 2 periods year by year. So basically, 1979 will be compared to 2029, and so on for 30 years. And we will see how those variations year by year are distributed. And in order to be able to compare all the indicators side by side, this time it will not be there will not be absolute comparison in, let's say, millimeters or number of days, but in relative variation. So basically we have the variations in percents for each indicators, so which will enable us to plot them side by side as box plots. This is what we are doing here for the Mediterranean region. So here is a reminder of the region that we are studying. And here are the relative variation in percent of our indicators, so SZII, Air 20mm, and RX 1 day. And you can see here for the mean precipitation indicator that in our future projections, well, the median value here is a decrease in mean precipitation by around 10%, maybe a little less. But depending on the year, it goes up to, I would say, 18 or 19%, minus 18 or minus 19%, to over a little over 0% here. But here in the RX 1 day and the R20mm, we can see strong variations. Here we have a median variation of approximately, I would say, 55% less of very heavy rain days in the Mediterranean region. And also the maximum of precipitations over 1 day also decreases, well, as a median value, by approximately 30%. And you can see that depending on the year, we can have up to minus 80% in frequency of very heavy rain days, and 40% less intense maximum precipitation over a year. So combining all those indicators, we can see that we have indeed less extremely intense precipitation even in this region, but also the simultaneous decrease in mean precipitation would indicate that well, this region could be more subject to droughts and dry days, and this would be like the opposite impact of climate change over this region than in Southeast Asia, for example. And there are actually in the climate indicators indicators that are used to compute extremes of well, absence of precipitation, so dry days, consecutive dry days, length of droughts, etc. So you can also try to compute them and compute them on the Mediterranean to see if you have results that are consistent with those ones. And I think we are reaching the end of this training. So as you can see, we have focused on analysis on precipitation patterns and how they compare in well, simulated future climates. Here are a few exercises that you can do, so you can try to explore the indicators at other dates when we first drawn the maps. You can rerun this analysis here on another region and see what you can find, perhaps Southeast Asia, to see, well, you should have a lot of different results than with the Mediterranean. If I do this right now, you will see that it is a lot different, with a strong increase in all of these indicators. And as I mentioned, there are a lot of different indicators that are available and described in this library, and you can try to compute them on your own and see if and this will allow you to expand the analysis and have well, more precise and consistent interpretations of those simulated future climates. And of course, we've studied precipitations, but there are also plenty of interesting analysis to make with temperature, winds, which also have their own extreme indicators. So feel free to retrieve data, just changing the variables in the requests, and you should be able to perform those analyses on other geophysical parameters. So this is the end of this training. I hope you enjoyed it, and